All right, here in section 2.7, basically what we're going to talk about is the same thing that we have actually in other sections. We're still talking about velocity and acceleration, except it's important that we can recognize it when we start looking at graphs as well. So you guys know from the stuff that we've been doing that velocity is basically position divided by time, right? So it's position divided by time, but we also need to be able to recognize that when it comes to a graph. So if you were to see a position versus time graph, and time's always going to be down here on the x-axis because that's your independent variable, and position's up here on the y. So when we look at this, this is doing nothing but showing me my position versus my time. Well, position versus time is simply what we call velocity. So here, this straight line would be the velocity of whatever my object is. Now, in this case, it's constant velocity because we have the same slope throughout. It doesn't always have to be constant. In this case, it is, okay? But all you're doing is you're looking at the slope of position versus time, and whatever that slope is, that is what is going to be considered your velocity, okay? Down here, it says example 15. A bicyclist maintains a constant velocity on the outgoing leg of a trip, zero velocity while stopped, and another constant velocity on the way back. Figure 2.18 shows the corresponding position versus time graph. Using the time and position intervals indicated in the drawing, obtain the velocities for each segment of the trip. Okay. So here's what 2.18 looks like. Well, this is him going wherever he's going. They say this is the way. This is his position versus time going out. So he would start wherever he is, right? He's starting at time 0 and position 0, and at some 600 seconds in, right, he has gone 1,200. Now, his position is 1,200 at this point in time. So, and this is in meters. So it has taken him 600 seconds, right, 600 seconds to travel 1,200 meters. Well, you would simply take 1,200 divided by 600, because position versus time, and that would give you the velocity. Or we could simply look at this portion of the slope right here. And if we look at the position of this, or the slope of this line right here, right, if you look at this, basically that's going to tell you, that slope is going to tell you what the velocity is. Now, you're going to say, but wait a minute, all they did was they took 400 over 200. Well, yeah, that's fine, because you can actually find the slope anywhere on this line, and it's going to be the same. So doing this, 400 over 200 is the same as if we'd have taken the bigger triangle and we'd have said 1,200 divided by 600. It's going to work out either way, because notice that they're the same right triangle. One's just bigger than the other one, but they're still going to have the same slope. So that's that's his velocity on the way out, right? The velocity on the way out, which is going to be a positive. And remember, velocity can be positive or negative, right? Velocity could be positive or negative because it is a vector. So in this case, this is going to be a positive velocity. And then he takes a break. So from time 600 to time 1,000, notice that his position is not changing at all. So basically, if you were to look at this from the standpoint of position over time, you would essentially have position all over time, which would be 400, right? So 0 divided by 400 is still going to be 0. So his velocity right here is 0, obviously, because his position is not changing. Give me 1 second, because I want to make that smaller. Okay, so that's that portion of it. Now, notice over here, now this is the part by which he is now leaving and he's heading back to wherever he started to, whatever that may be. So this is why he's going backwards, right? Negative velocity, because he's actually heading back to where he started. But notice he does not get clear back to where he started, right? They stop it at position 400, which is fine. So in this case, again, they do just a portion of this right here. So they go negative 400 divided by 400. But we could have also done the bigger triangle, right? We could have done this clear over here, bring it clear down here, and find out what the difference, what my change in y over my change in x is. And that's fine as well because it's the same slope everywhere. So you could have done the bigger triangle, you could have done the smaller triangle, but no matter what, you're still going to get that right here, he has a velocity of negative 1 meters per second, right? Again, because velocity is a vector, and that's why that one's negative. Over here, we had a velocity of 2 meters per second positively, and this one we said was 0. Okay, so that's just looking at it from the standpoint of graphically finding velocity, I guess I should say. Now, we did discuss this whole notion of average velocity versus instantaneous velocity. And instantaneous is as your time period becomes very, 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 very small. Well, this here is going to have to be more of the average, right? Average, because you're talking a pretty large time period on both of these, right? So this would be more of an average, whereby if we were to look at this one down here, these are just giving you what I already said, the 2 meters per second, 0 meters per second, negative 1 meters per second. If I was to find instantaneous velocity, right, instantaneous velocity, I would want to be looking at a much, much, much smaller time period. So you let your time period get very, very small, and that's how you're going to find instantaneous, okay? As a matter of fact, it's like looking at one single point on a graph and looking at the tangent line right there. And this is that whole notion of limits where you're letting your time approach 0, a very, very, very short period of time, okay? And if you are looking for your instantaneous velocity right here, you would simply draw a tangent line and find the slope of that tangent line. Suppose I wanted to find it, if I wanted to find the instantaneous velocity right here, well, I could still do that. Let me put this in red so it's more easily seen. I could find the instantaneous velocity right here. It's just I would have to draw a tangent line right on that, and then I would have to find my slope here in order to find out what my instantaneous velocity is right there, okay? So a little bit different than above, the difference between instantaneous velocity and average velocity. Let me move down just a little bit. Then they talk about the slope of the line in the velocity versus time graph is your average acceleration. Well, that only makes sense because, look, if a minute ago, right, we were talking about position versus time, and we said that that's velocity, then it would only make sense that if I had a velocity versus time graph, right, that's my average acceleration. So because we've talked in previous sections about acceleration being my change in velocity all over my change in time, that was acceleration. Well, then it only makes sense here that I'm talking about velocity versus time on a graph, finding the slope of that, and this is going to be my average acceleration, right? This is going to be my average acceleration right here, whereas on the previous page, we were talking about position versus time, and that's velocity. So really nothing has changed here from previous sections. It's just now we're trying to look at things from the graphical standpoint. Notice here we have units of meters per second because that's what velocity is. Well, meters per second divided by a second would be a meters per second squared, so our units still work out. And that's just looking at velocity and acceleration graphically.